10.1 is our next section. So chapter 10 is about correlation and regression. We are only going to do 10.1 and 10.2, which these concepts you've actually learned before in algebra. So let's go over some things. So we introduce the linear correlation coefficient R. Linear correlation coefficient, which uses the variable R. The correlation coefficient measures how well a paired sample data fit on a straight line pattern when graphed. We use a sample of paired data, sometimes called bivariate data, to find the value of R, and then we use R to decide whether there's a linear correlation between two variables. So we will have like a table X and Y collecting data, and then use that data to find out how well the data is correlated. We consider only linear relationships, which means that when graphed in a scatter plot, the plots approximate a straight line pattern. So this is stuff we've already done. We've done this in college algebra. You did this in Algebra 1 and Algebra 2. Then we discuss methods. So this is where it goes into more of the statistics side. We're going to discuss methods for conducting a formal hypothesis test that can be used to decide whether there is a linear correlation coefficient.
Released all of the softball girls down to the field.
So we'll do hypothesis tests with this. Normally we just say if R is close to 1 or -1, then it's a good correlation, but we're actually going to have a number which is a critical value. So a correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between two variables when there's a correlation and the plotted points on paired data results in a pattern that can be approximated by a straight line. We use the linear correlation coefficient R, which is a number that measures the strength of the linear association between two variables. So here are some examples of correlations. So this is a positive correlation because it has a positive trend, negative correlation, negative trend, no correlation because it's all over the place, and this is non-linear. The closer the values are together, so if you look at these are both strong correlations, but because these are more clustered together, it is closer to -1. This one is close to 1, but not as close. So a number that's close to 1 is considered very, very strong. The further you get away from 1 or -1, the weaker it is. So given any collection of sampled pair quantitative data, the linear correlation coefficient R can always be computed. But the following requirements should be satisfied when using the sample paired data to make a conclusion about linear correlation in the corresponding population of paired data. So the sample of paired XY data is a simple random sample. So the data must be collected as a simple random sample. Then whenever you graph it on a grid, it should look like a straight line. So it should approximate a straight line. And outliers greatly affect our graph and also the R. So if you know that there's a known error, then you want to make sure to remove that. So because the results can be strongly affected by the presence of outliers, any outliers must be removed if they are known to be errors. And we can use the calculator to check the 2 and 3 actually. So what's important about the correlation coefficient R is that R is always between -1 and +1. So if you look at a number line, you have 0 in the middle, 1 on the right side, -1 on the left side. And it measures the strength. Normally we say just something close to 1 is considered strong or something close to -1 is considered strong. But today we are actually going to be looking at it more statistically, and we're going to have critical values that we look at. So all of the values, if all the values of either variable are converted to a different scale, the value R does not change. The value of R is not affected by the choice of X or Y. You can interchange X and Y, and the value R will not change. R measures the strength. It's not designated or designed to measure the strength of a relationship that's not linear. So we're just looking at a linear relationship. And R is very sensitive to outliers. So the importance here, you can interchange X and Y. You can convert to a different scale. R won't change. And it's always between -1 and 1. We are going to round R to 3 decimal places, so we can compare to the critical values. P-value from technology to interpret R. Use the p-value and significance level as follows. Alpha. P-value is less than alpha. It supports the claim of linear correlation. Usually we use 0.05. So we're going to look at the p-value and compare it to 0.05. And if the p-value is less than, then it supports the claim of linear correlation. If the p-value is greater than alpha, then it does not support the claim of linear correlation. In college algebra, we put the data into L1 and L2, and then we went to linear regression. But we are not just looking at the equation. That's actually 10-2. We'll look at just the equation. But right now, what we're looking at is R, and we're also going to look at the test statistic. So see how this says linear regression t-test? So this is found in the test. So if you go to stat test, I think it's down toward the bottom, so I just went up. Linear regression t-test is F. So make sure you know, you'll go to stat, over to test, and this one is found F, which is linear regression t-test. You can't see that. So there's 2 ways to determine correlation. You can look at the p-value, compare p-value to your level of significance, or you can look at your test statistic, do your critical values, and compare it that way. So we're going to look at p-value first. So to find your p-value using technology, so we are going to go to second bars, which is distribution, and go to TCDF. And you'll want to use your t-value to determine your p-value. So if I have this, let me see. I think I might have some statistics in here. Let me see. Yeah. So I have this random one. This one is linear. Then I would go to stat, over to calc, and then over to test. Linear regression t-test. Let's say I'm using the not equal to. So it'll give me the t-value, which, see, the t-value is 10.456. And so I use this t-value from my linear regression to find the p-value. So I would go to TCDF, and it was negative 10 point, what was it, 9? Did y'all pay attention to that one? Something like that, to 10.9. Degrees of freedom. Actually, for degrees of freedom on here, you'd have to know how many there are, how many data points there are, so we'd have to look. So we'll actually do that on an example. We can also use table A6 to interpret R by looking at your critical values. So I actually included this in y'all's notes. It's on page 6. For degrees of freedom of critical values, we're actually subtracting 2. Which this one just gives us n. But for degrees of freedom for your critical values, we're going to subtract 2. But this just gives us n, so we're good there. All right, let's look at the next thing. Test statistic. The same method of part 1 can be used for the test statistic R. And the test statistic can be used by following that with n minus 2 degrees of freedom. So we'll use that. Correlation is you compare your R value to your critical value. If, let's say we have 0, we have negative 1. If R, let's say this is my R value, and then say this is my critical values. See how it's above the critical value? This critical value determines what is considered strong. So anything above the critical value on the right side, positive side, is considered strong. Anything below the critical value on the left side is considered strong. But if I have, I'm going to use a different color. If I have that another value, this is R. This means no correlation if the R value is right there, because it's not beyond the critical value. It's in between the two critical values. So anything in between the two critical values is considered weak or no correlation. Anything between here. But above it is considered correlation or strong correlation. So anything to the outside of those critical values. So if R is greater than the critical value, then we can support a linear correlation. If R is less than the critical value, then there is not sufficient evidence to support the claim. Okay, let's go to our example. Okay, is there a linear correlation? So what this data is, it came from our textbook that we really haven't used all year, but it comes from the textbook. It is talking about chocolate and Nobel Prizes, which seemed like there's no even association there. But anytime you compare two things, an X and a Y, you can look for some kind of correlation. So we need to check our requirements. So is it simple random data? Yes. Let's look at how we can check our graph. So what I want y'all to do is put this into L1 and L2. and we'll review how to put it on a scatter plot like this. Once you put them in, go back and make sure you did it correctly. So let's review how to put it on the graph. I want to make sure I have nothing in the y equals that'll interfere. You go to second, y equals, which is stat plot. We want to turn the plot on. And you can change these, but the first one's scatter plot, so that's what we want. You can change what color if you want. And then we need to hit, if you hit graph, you may or may not be able to see all of them. So what you want to do is you want to go to zoom, and you want to zoom to the statistics that you have in. So it's number 9 for zoom stat. And then it comes up with the graph in a way that you can see all of them, all of your points. So is it an approximate straight line? Well, does it follow a straight line pattern? Yes. Yeah, it follows a straight line pattern. So let's put a check mark there. It doesn't go like, let's see. It doesn't go like that, right? That would be a non-linear. So it's in a linear pattern. Okay, we don't know if there's any errors, so there's really nothing we can do there. All right, check that off. Okay, so we want to use p-value from technology to interpret R. So we need to go to the instructions, which were stats, over to test, and then linear regression t-test. Way we can get some information. And we're going to use the not equal to. It's either correlated or it's not. So we're using not equal. Okay, let's calculate. Okay, so it gives us a lot of information. It gives us t, 6.123. It gives us degrees of freedom. There are actually 23 pieces of data on here, paired data. So our degrees of freedom is 23 minus 2, which is 21. Let's also look at R. R is 0.801, because remember we're supposed to round to 3 decimal places. We're not going to worry about anything else right now, just those things. So to find the p-value, we are going to use the information we have and do that TCDF. So second distribute vars, do TCDF. And we are going to use the t-value as our upper and lower bounds. So negative 6.123 and positive 6.123. Degrees of freedom is 21, sorry. All right, so it gives us 0.999999. But remember, that's everything in between. So with this TCF, it's everything between there. But we want to find what this is. So we're going to subtract from 1. So do 1 minus that. Which would be a really, really small number because it's e to the negative 6. So that actually means I would move my decimal over 6 places and put zeros in there. So my p-value is 0.000. 0.000. And I'm comparing that to 0.05.
Look, mine gave me the p-value when I did the t-test.
What was the p-value?
4.477 e negative 6.
That's not the right. That's p. That's not the right p-value. It's a different value because, oh, did it? E to the negative 6?
-6.
No way. Okay. So it actually does give it.
The fourth decimal, it's a 4, not a 7.
Oh, so it actually gives it to us. That's great. Okay. So we didn't have to do that extra step. We could have just found it. 0.000. Awesome. Glad you saw that. Yep. Good job. So then the p-value is 0.000 when rounding. Because the p-value is less than or equal to significance of 0.05, we conclude that there is sufficient evidence to support the conclusion that for countries that there is a linear correlation between chocolate consumption and Nobel lecturines. Lecturettes? I don't know how to say that word. Do y'all? People who receive Nobel Prize, I think. Okay, so that was an easy way to find it. We didn't have to do TCDF because it gave us the p-value. So let's look at the other way to interpret it. We need to find the critical value. So the critical value comes from the table. So look at the table. It's table A6. And there's 20 something. And this says N, so it'd be 23. So it's a value between these two. So we can't find the exact value. So let me see. The ones that you'll have on your assignment will have an exact value on there. So the way that they estimated it on this example is 0.413. So see the critical values are on the number line with 0 in the middle. So anything between your critical values is no correlation. If it's beyond the critical values, it is a correlation. So because our R, the value that we found earlier, 0.801, is beyond our critical value, then that means there is a correlation. So because the figure shows that the computed value R equals 0.801 is greater than the upper critical value, we conclude that there is sufficient evidence to support the claim of a linear correlation. So there's two ways to look at p-value and then your critical value. Okay, we'll also look at R squared, which when we did the value, we found R is right there. R squared is whatever R is squared. So see how 0.8 and then R squared is 0.64. So what this tells us is we conclude that 0.64 or 64% of the variation in the numbers can be explained by the linear relationship between chocolate consumption and Nobel Prizes. So this implies that 36%, so the opposite, the complement, 36% of the variation can be explained by rates of chocolate consumption. So 64%, which is R squared, explains the variation. So R squared explains variation. 1 minus the R squared explains implies that 36% of the variation numbers cannot be explained by the rates. So, and something important to remember, I know in Algebra 1 I teach this a lot, correlation does not imply causality. We noted previously that we should use common sense when interpreting results. So clearly, it's absurd to think that eating more chocolate would help you win a Nobel Prize. But we are able to look at the association between them. So here are some common errors. Just read over those. And then the formal hypothesis test is, like I was saying, your null hypothesis is that P equals 0, which means no correlation. And then the alternative hypothesis is P does not equal 0. This is a two-tailed test. Two-tailed. Because we're looking at the two tails. The two tails imply correlation. What's in between your critical values is not. So the examples and exercises in this section generally involve the two-tailed test. But one-tailed test can occur with the claim of positive linear correlation or the claim of negative correlation. So this is if you were looking at P is less than 0, that would be your negative correlation, or P is greater than 0, that's a positive correlation. Okay, let's do 2 examples. Go ahead and read over the data and what it's talking about. So I put my information in L1 and L2. And we just want to know, is there a correlation? So we're using the two-tailed test where we're going to say not equal. So our null hypothesis is that that value equals 0. And then our alternate, that value does not equal 0. So it's that two-tailed test. Let's turn our plot on and let's look at it and make sure it looks somewhat linear. And it does. So just kind of construct some points. So I kind of just put little dots, kind of estimated what it looks like. And then go back to our linear regression t-test so we can get all of our information from here. So R is 0.857 as we go to 3 decimal places. Test statistic T 4.406. What is the P? 0.003. So we are going to look at it p-value and compare it to that level of significance. So p-value versus our significance level, 0.003. So it is less than. So anytime you're less than 0.05, that means there's a correlation. Because the p-value is less than the significance, 0.05, there is sufficient evidence to support the claim that there is a linear correlation between court incomes and justice salaries for a significance level of 0.05. And what we are looking at, does it appear that justices might profit from levying larger fines? So because there is evidence that there's a correlation, yes, it appears that justices might profit by levying larger fines. Look at example 2. Inside here, these values represent R. It says correlation matrix. So the correlation between glass and paper is 0.312. The correlation between paper and glass is 0.312, which it doesn't matter which one you use as X, which one you use as Y, you still have the same correlation. So let's write the null and alternative hypothesis. So it's going to be a two-tailed test because what we're wanting to decide is we want to look and see if there's enough evidence to support a linear correlation. So equals 0 and does not equal 0. On this one, we need to look at the table. So the data set includes weights of garbage for 1 week, 62 different households. So that's N. N is 62. So let's look at what we can use here. So we're going to use the closest number. So 2.254. See how that's the significance of 0.05? This is the one that we'll usually use. in all of our problems right now, we don't use 0.01. So we're going to use significance of 0.05. So 0.254 is our test critical value, right? Isn't that what it gives us? 0.254. Okay. So what we want to do is we want to put this on a number line. 0, -1, and +1. And our critical value is plus minus 0.254. So this would be right around here, 0.254 and negative 0.254. So anything between it is no correlation. I just put none. And anything beyond it is a correlation. So 0.3218 actually falls above it. Even though that seems like a low correlation compared to what we're looking at with 62 data values, it's actually going to be considered a correlation. So because the absolute value of the test statistic is greater, I should have said greater, sorry, greater. The positive critical value, greater than the positive critical value, there is sufficient evidence to support the claim that there's a linear correlation between weights of discarded paper and glass. The test statistic T is the R value. It's the 0.3218. So we'll finish 10 to next lesson.